The sampdistC function has two required arguments, stat and se. The stat argument is set equal to a sample statistic, and se is set equal to that statistic's standard error. Both values should be single numbers. If the standard error isn't given to you in a problem or exercise, you may need to calculate it using the appropriate formula to supply it to the sampdistC function. The sampdistC function supports some standard optional arguments. With sampdistC, you have options to specify the number of digits you want to see after decimal points, and whether you want to print your results to an HTML file in your working directory. You can set the function's optional t.df equal to a whole number to use a t-distribution rather than a normal distribution. You can set plot.cdf equal to true to obtain a cumulative density function rather than a probability density function. The sampdistC function automatically calculates 95% confidence intervals, but you can set the function's optional ci argument equal to another confidence level to calculate other confidence intervals. To learn how to use the sampdistC function, let's work through some examples. I'd like to show you how to use the sampdistC function in the RCPA3 package. Before the video started, I've installed the RCPA3 package, used a library command to load it in this session, and then ran this help sampdistC command to pop up the documentation for the function in the help pane over in the lower right. So this function really isn't used for analysis directly per se, but it can be very useful to help you understand the results of your analysis or what you're looking at in an analysis, especially when you get into inferential statistics. Inferential statistics can be kind of abstract and less concrete than descriptive statistics, and I think that it can be helpful to work with sampling distributions, some trial and error, trying some different numbers and manipulating them to get a hands-on feel for what they look like, their shape, what you expect to see. And I think if you do that some, like with the sampdistC function, the results of results of political analysis, particularly with inferential statistics, make more sense. So let's just type in the sampdistC function, and I'm going to input the required arguments to show you what it will generate for us. So the function has two required arguments, stat and se. The stat argument is just set equal to a single number that would represent like a statistic from a sample. Say, I'm making up these numbers just as a hypothetical. This is just coming out of my own head right now. So let's say we conducted a survey and we found that the survey said that 0.65 of respondents had a particular opinion, and we calculated the standard error of that sample statistic to be 0.04. So the typical amount of deviation from the parameter would be 0.04. What would that look like if we were to repeatedly conduct samples, so to collect many samples or many sample statistics? I put this into the sampdistC function and it returns this result. This is showing us what the distribution or the sampling distribution, the distribution of the sample statistics would look like. It centers on 0.65, that's the expected value, and the standard error is 0.04. So the gray area is plus or minus 1 standard error, and the pink area is from 1 to 2 standard errors away, and then the red area is 2 to 3 standard errors away, and the very dark red area is 3 or more standard errors away. This is the normal distribution. We would expect this statistic to follow a normal distribution and then have these properties indicated on the plot. that 68% of the repeated samples, or 68% of the area of the distribution, falls within plus or minus 1 standard error, which would mean if 60% is in the gray area here, that 16% is below that area, 16% is above that area, and so forth. Between plus or minus 2 standard errors, we see 95% of the distribution, so 2.5% of the area is greater than 2 standard errors, 2.5% of the area is less than 2 standard errors. And so this is what we would expect to see given these numbers. But if the numbers were different, say we were, I don't know what else we were measuring, say like a feeling thermometer score, and we asked respondents how they felt about a subject, and the average was 63, and the standard error of their responses was 4. I'm just making up the numbers here. What would the expected distribution of the sample statistics look like? Well, we see another figure. Now, don't let this kind of fool you here, because the shape is always going to be this normal distribution. But the thing that really changes here is the x-axis for the scale of the distribution. On the last figure, I mean, the scale goes from 0.5 to 0.8. It's just a 0.3 difference between them. But given the new numbers, the scale really is going from like 45 to 80, a much larger scale, because the sample statistic is a larger number and the standard error is a larger number. So this scales up given the sample statistic, but the overall shape is going to be the same. So this is what we would expect to see in repeated samples. Another way to look at it, the function also reports the confidence interval of the sample statistic, and it reports the point estimate 63, which would correspond to the statistic, and then the lower bound and the upper bound. And this is for the 95% confidence interval, and it tells us the lower bound is 55.160 and the upper bound is 70.84. So 95% of the area should be between 55 and 70. And the neat thing about this, I think it's a neat thing anyway, is if you look at the plot we created, you can see where this lower bound is and where the upper bound is. And you can see, hopefully, why it's the 95% confidence interval. That's where the separation between the red area and the pink area. This line separating the red from the pink is at 55.16. And on the other side, the line separating the pink from the red is at 70.84. And it's a 95% confidence interval because 95% of the area is between 55.16 and 70.84. That's why we call this the 95% confidence area. And one way to think about it is if this were the sampling distribution and we were to conduct a random sample, how confident would you be that the statistic from that random sample would be between 55.16 and 70.84? Well, it's not always going to be. There's a chance that it's going to fall outside that area, but you would be 95% confident that that next random sample statistic would be in this middle part of the distribution. That's where it usually occurs. So you would be 95% confident that the sample statistic would fall in the 95% confidence interval. Well, I left off looking at the sampling distribution for the statistic 63 with the standard error of 4. And this, as you can see from the main title, shows a normal distribution of the sample statistic. One option you have with the sampdistC function is to show the expected distribution based on t-distributions instead of the normal distribution. What you would do for that is to use the t.df argument and set that equal to a whole number. For example, and I'm just making this up number, is the number 29. So we're saying what we'd like to see the expected distribution based on a t-distribution with 29 degrees of freedom. That's going to be a distribution that's a little bit more conservative, I would say, with respect to inferences. And let's run this and see what the t-distribution looks like compared to the normal distribution. Should be similar, but with some important differences. Now it's pretty subtle, but there are some changes to the plot. With the t-distribution, if you compare the middle part of it, less of the area is within one standard error. With the normal distribution, it was 68. With the t-distribution with 29 degrees of freedom, slightly lower, 67.4. So the mass of the distribution is fanning out a bit. The tails on the left side and the right side are going to be a little bit heavier. And you can see that with the 95% confidence interval based on the t-distribution with 29 degrees of freedom. The lower bound is 54.819 compared to 55.160 with the normal distribution. And the upper bound is a bit higher, 71.181 compared to 70.840 with the normal distribution. And I said I encourage you to kind of play around with the function to see what happens. For example, if you lower the degrees of freedom further, a little bit less of the area is in the middle. Now we're down to 67% of the area, and notice that the bounds of the confidence interval change as well. The lower bound is lower than it was before, and the upper bound is a little bit higher than it was before. And it definitely is higher, the upper bound is definitely higher than the standard normal. So the more we lower the degrees of freedom, the more the expected distribution spreads out. You can also think about, what happens when you change the standard error. It's showing it at 4, but what if it were 5? The shape looks the same, but it's the shape overall is the same, but the scale at the bottom is changing, and you can see that with the confidence interval even better, where the lower bound is lower than it was before. It's now 52.5. Before it was 54.6, and the upper bound is even higher now, 73.465 when it was 71.372 before. So the higher the standard error, the more spread out the distribution is, the wider the confidence interval becomes. So I think that's kind of a way that you can kind of work with and play with sampling distributions to see what expectations you have about sample statistics. Another argument that's useful for the sampdistC function is plot.cdf. By default, this is false, and it will show you this shape. It's called a PDF, a probability distribution function. But we can change plot.cdf to true to get a different look at the same distribution. So now this shape, this sort of like S-shaped curve, is showing us the proportion of mass of the distribution we would expect at different values. So at 63, the point estimate, the middle of the distribution, is the 50% value. We would think that 50% of the distribution is less than 63. And if you look at the PDF, that seems to be true. At 63, about half, exactly half of the distribution is less than 63. And say at a number like 52.535, which is indicated with this faint red dashed line, only 2.5% of the distribution is less than 52.53. That's the value for the left tail. And then the upper bound of the confidence interval, 73.465. The other red line is the upper tail, and only at this point it's 73.465. We've achieved 97.5% cumulative density, or 0.975 cumulative density. And the very faint, if you can see it, the very faint dark red line would be the 99% confidence interval, the 1% significance level. Very high on the scale and very low on the other side. So almost all the distribution is contained between the 99% confidence values. And so you can see what that would look like. You could also take this off if you want to return to a normal distribution instead of a t-distribution. You can also see it's CDF. And the overall shape should look similar. It will look similar, except the scale is going to be different. Now, I talked about that 99% confidence interval, kind of speculated where the values for the lower bound and upper bound will lie. If you want to see that more explicitly, you can use the CI argument to specify the confidence level as a percentage. So by default, it uses the 95% confidence interval, but if I did want to see, say, that 99% confidence interval, I could add the argument CI equals 99, and now I'm seeing the 99% confidence interval. And that 99% confidence interval should be wider, and you see that here. The lower bound is lower than the lower bound of the 95% confidence interval, and the upper bound of the 99 is higher than it is with the 95% confidence interval. Now, if you like, the sampdistC function has the print_c argument. It's by default false, but you can set the print_c argument to true if you want to output the table of the confidence interval and the plot to an HTML file in your working directory. It also has the standard digits argument if you want to change the number of digits displayed after the decimal point in the table. By default it's 3, but you could make it more than 3, or you could make it less than 3. I think one particular useful utility of the sampdistC function is to solve those problems that give you a sample statistic in its standard error, or the information needed to calculate its standard error, and ask you to generate the confidence interval for that statistic. So the sampdistC function can do that. Like, for example, if you had a problem that said, say, 38% or 0.38 of respondents favor a policy, and the standard error of the estimate is 0.3, what is the 99% confidence interval? I'm just going to omit the plot CDF argument because we really don't need it. What is the 95% confidence interval? You can input that information like from the problem, 0.38, a 0.03 standard error, and the 95% confidence interval, and run it and use the sampdistC function like a confidence interval calculator, because there are some problems where you're not generating the statistic and the standard error from a data set, but you can be supplied the standard error and the statistic in the problem, and the sampdistC function is useful if you are given the statistic and the standard error and want to find its confidence interval. So like in this instance, the confidence interval for 0.38 with a 0.03 standard error would be bounded between 0.321 and 0.439.